Composite deck, as I think most of you know, it comes in standard 1.5 inch depths, 2-inch depths, and 3-inch depths. The code, the ISC specification actually limits us to 3-inch decks for composite action because there just hadn't been any tests. I think we're in an area now where we ought to really be looking more at using deeper decks. And I want to talk about that more under the roof decks because I think that's where it really applies. But we're rapidly moving into a condition in structural steel design where labor is becoming a more and more important component of the cost compared to the material. Every year that I've been in practice, the material prices are going up at one slope and the labor prices are going up at a steeper slope, until eventually the labor is going to dominate the cost and the material is going to be secondary. We're almost getting to that point right now where even though the cost of structural steel, raw structural steel, is going up, the labor costs are going up a lot faster. So the old adage about least weight is least cost is certainly not true anymore at all. I think the price of steel, fabricated and erected steel today in place, is more a function of the cost per man hour rather than the cost per pound. And contractors are still duped by this. They look at a design and they say, well, wait a minute, this design is 12 pounds a square foot and this one's 14, so I picked the 12. When in reality, what's really going to dictate that is not the 12 versus the 14, it's how many man hours per ton and dollars per ton is in the labor components to produce those two systems. That is the fabrication, the shipping and the handling, the erection. That's much more important than what is the raw material cost. So I think all of us engineers need to quit thinking least weight is least cost. We need to be thinking of structural steel today is more about how many pieces are you erecting, how many pieces are you fabricating, as opposed to how much do those pieces weigh. So one of the ways to reduce our piece count, and I'm always being reminded by erectors, you know, boy, if you could come up with a system that cuts the number of pieces I have to handle by a third or a quarter, then you're going to see some meaningful reductions in erection costs. So how can we reduce the number of pieces? Well, we can get decks that span further so that we can reduce the spacing of the purlins, the roof purlins, and the floor beams, and cut down the number of those elements. That reduces erection costs, more so than designing a lighter beam. So I think there's a market out there for heavier decks spanning longer distances for roof construction. And I know there's some manufacturers that are looking hard at that. The downside of that is that when you start getting deeper decks that are heavier gauge, just the manhandling of the deck itself, sheets, by the crane gets to be a problem. Right now with 2- and 3-inch decks, 2 men can be on each end of the crane that's lifting the sheet and manhandle it to the steel frame and hold it down. When you get 7-inch decks that are 15 gauge or 16 gauge, those decks become very heavy and 2 people can't handle it anymore. So that's a counter issue that has to be dealt with. But the fact of the matter is, limiting ourselves to 3-inch roof decks, I think, is probably hurting us in terms of achieving the lowest cost, lowest in-place cost of the frame. This slide just shows that there are other non-composite or other composite deck types. The regular composite deck that we've been talking about, but then there's also the cellular decks that are still somewhat popular for office buildings when they need the underfloor access. And then, of course, they got special decks like the Epic deck where you can hang things from special hangers and slots in the deck. Those Epic decks, for those of you who haven't used them, I think are very nice decks, but they're also very pricey. Most people are very proud of their deck. We talked about, I think, most of this as it relates to composite deck. You've seen this same table before, where it's just nothing more than a function of the deck depth, the type of concrete, lightweight or normal weight, the hourly rating you need, and what stud is recommended for that assembly. That's what this slide's all about. You saw this slide before where it also gives you the recommended spans for different types of deck that are carrying different floor thicknesses, either normal weight or lightweight concrete. Just a point of observation, and I'm sure many of you all have noticed this too. I've never found it economical to go any heavier than an 18 gauge deck. 20 gauge, yes. 19 gauge, yes. 18 gauge, yes. All of a sudden, when you get to 16 gauge, the price, for some reason, just goes up dramatically. It must be involved in the manufacturing process. Maybe I should ask somebody at AISI who might know the answer. But anyway, the thicker, heavier deck seems to be really a jump in cost, so they just never price out, even though I'd love to get a 16 gauge deck and use it to span further. It just, the cost premium is very high. The Steel Deck Institute publishes a design handbook, and probably many of you have on your library shelf, and I'm sure you can get it online now, that gives you all the ins and outs of designing with metal decks, composite deck. Be careful when you're using the deck catalogs, the composite deck catalogs. Some of them now are being set up for ASD, some of them for LRFD. And you can get additional capacity out of those composite decks if you use a plastic stress distribution concept that requires some additional studs on the composite beam to take advantage of that additional strength. So be careful if you're using an LRFD catalog that has that load capacity built into it, that you conform to the stud requirements in that design. There are design aids out there. This one comes from the Steel Deck Institute Composite Deck Design Handbook, 1997, that gives you shear and web crippling capacities for the deck. It might be important if you have heavy concentrated loads that you have to design for. Notice that both ASD and LRFD is covered. There's also a nice provision in the Steel Deck Institute catalog for designing for heavy concentrated loads. This is a snapshot taken directly from the deck catalog. It's their figure that basically says if you have a concentrated load that's B2 by B3 in width, that causes a stress pattern in the slab in each direction. And using some finite element modeling techniques, they came up with some recommendations on how you reinforce that slab for moment perpendicular to the span of the deck, because it obviously is going to flex some, even perpendicular to the span of the deck. So they give you effective widths to design for. I'm not going to go into this. You really got to study it a little bit to understand what it's all about. But just to be aware that it exists, if you do have a 10,000 pound concentrated load on a composite slab with a fairly small footprint, the Steel Deck Institute does have a design procedure you can use to check punching shear, check one-way shear, and then check flexural capacity, and gives you guidelines on how to reinforce that slab accordingly for that heavy concentrated load. It's all a function of B2, that's the width of that's the loading footprint that's imparted on the slab. Knowing that, you project that cone downward to the bottom of the deck to get this B sub m distance. So B sub m takes on an equation that it's the form of the thickness of the concrete and also the thickness of the topping, if you have, if any. And that B sub m equation, or that B sub m value, is kind of like an effective width that you plug into this effective width equation to get the effective width for shear and moment when you're checking the capacity of the deck. And then the W distance that we saw here, that W distance is the effective width over which you put additional reinforcing in the slab for flexure to handle the bending moment in the direction perpendicular to the flutes. So anyway, it's just a good, convenient way to handle what before you were pretty much on your own on how to deal with this. Now the Steel Deck Institute has come up with a rational procedure to use in design. Okay, let's talk about composite deck finishes. Many of you have probably seen the term G60 and G90. Those are just galvanized coatings. G90 being a heavier coating, more appropriate for a more severe environment like a roof construction where you might have water surrounding that deck, where you want to have a little bit more resistance to corrosion, particularly remembering if you're using that slab as the positive, or that deck as the positive reinforcement, you don't want it to corrode away because then you have no reinforcement. So the selection between G90 and G60 versus a painted finish may be an important consideration from a corrosion standpoint. Different engineers have different rules. We like to use, for all roofs, we like to use G90. For floors, we're willing to drop back to G60 or even a phosphatized painted finish if the owner understands that he's getting a lower cost for that deck, but he's also incurring a little bit of more risk for corrosion. But the risk for corrosion in the floor system is probably not that great compared to a roof system, so that's why in our practice we use the G90 for roofs, the G60 or the phosphatized painted at the owner's choice for floors. Remembering that the deck serves as the positive reinforcement, so that's why this warrants some serious consideration on the designer's part. There are design aids out there in the steel deck manuals. Mullcraft has one. You know, all the major deck manufacturers have them. This one is for slab edge pore closures, where you have a bent plate or a bent light gauge element cantilevering out, and that element has to serve as a form, cantilevering off that spandrel beam to carry the wet weight of the concrete and the potential of a man walking out there at the same time. So it gives you guidelines on how much load you can carry as a function of your cantilever distance. So that's a handy thing to use in the design and selecting the size and the gauge of that closure element. On to roof decks and non-composite decks. There's three primary types of non-composite decks: roof deck, vented form deck, that is decks that support lightweight insulating concrete, which are still fairly popular amongst a lot of architects. And then, of course, form deck itself, which is nothing more than the form for a concrete slab that's reinforced like a conventional concrete slab. First, roof decks. There tend to be three types: narrow rib, intermediate rib, and wide rib is how they're known in a lot of catalogs. Also known as Type A, Type F, and Type B decks in the manufacturer's jargon. And different decks are appropriate for different thicknesses of insulation and different spans. There's no one deck that is, quote, right. It depends on the thickness of insulation, because remember, the insulation has to span across the flute there, so you can only use the wide rib, which is probably tends to be more economical from a material standpoint, but it also means you have to have a heavier insulation that might span across that wider opening. So that's one of the factors. There's also a 3-inch deck, Type N deck it's called. And then, of course, there's cellular decks that many architects like in exposed conditions, like an auditorium or a school, where they don't want to buy the cost of a ceiling, a hung ceiling, so they use the deck as the finish. They put a nice finish coat of paint on it, and then they like to, when you look up, they like to see a nice flat surface or something that's more interesting than just an old ugly galvanized metal deck. But we see a lot of that in our school construction that we do, and auditoriums and that kind of thing. Form deck, of course, thickness above the concrete can range anywhere from as low as 1.5 inches to as much as 5 or even 6 inches. Form deck normally comes in various standard depths. 9/16 inch is what we used to call chloroform, or wrinkle tin as it's known on job sites sometimes. Then the heavier 15/16 inch deep flutes. Then the 1 5/16, 1.5, 2, and then even 3-inch form decks. We used to do millions and millions of square foot of schools in Houston, and the material of choice was always chloroform deck, 9/16 inch deep, with 2.5 inches of lightweight insulating concrete on top of it, and then a single ply membrane roof or a built-up roof. Millions and millions of square foot of roofs have been built with that kind of construction, and you still see it a lot. Still see a lot of insulating concrete roof systems. For construction safety, there's a requirement by Factory Mutual that says you have to take a 200-pound load per foot at mid-span, at the midpoint of one span, with a deflection limit of L over 240, and that drives you to these limits on span for the different types of deck: narrow rib, intermediate rib, wide rib, for the different gauges. So if you're going to conform to that Factory Mutual requirement, and by the way, that's an insurance issue, you need to talk to the architect, and who in turn needs to talk to the owner. Are you being insured by a Factory Mutual insurance company that warrants that we follow these criteria? And many times we ask the question and the owner doesn't know and the architect doesn't know, so then we're just left to do whatever we think. But you ought to at least ask the question. There are rules out there for attaching these decks to their supports, either by welding them or screwing them. Normally, if they're welded, it's with 5/8 inch puddle welds, although if you're in a seismic zone out in California, you frequently see them using 3/4 inch puddle welds to get additional shear capacity in their diaphragm. You can use powder or compressed air actuated pins. Power driven fasteners are common. Self-drilling fasteners. You need to be aware of what the requirements are, depending on whether you're following the Steel Deck Institute requirements, the Factory Mutual requirements, or you also need to pay attention to your diaphragm strength requirements. All of these are factors that go into the selection of how you attach your metal deck to the steel frame. Steel Deck Institute has their own minimum requirements. Absent anything else, this is what we always fall back to: SDI minimums. 18 inches on center in the field of the roof and 12 inches on center in the perimeter and corners if the rib spacing is less than or equal to 6 inches, otherwise at every rib throughout. You got to be really careful in hurricane regions for wind uplift. You can get enormously high uplift pressures on roof surfaces in hurricane zones, as we all have seen with the pictures of roof membranes being blown off. A lot of those problems are coming from the fact that the decks aren't being attached properly at corners and at eaves where the wind pressures get to be very high. So this is something we pay very close attention to in our spec. In hurricane regions, identified by either I-90, the Factory Mutual has their own class system, which is I-90, I-120, and so on. The higher the uplift rating, 90 means 90 pounds per square foot uplift pressure, which is very high pressure, representative of what you can get in a very high corner of a building in a very high windstorm. They get to very strict attachment requirements. And so you need to be very mindful of that if you're designing a roof in a hurricane zone where you want to build in that uplift resistance. Roofdeck Finishes, again, you can buy them painted, galvanized, either G60 or G90. And, you know, the manufacturers will give you a lot of options there. And, of course, the more exotic you get with the paint, the more expensive the deck is going to be in cost. Generally, when you're selecting roof deck, the steps are you choose the deck type and depth to suit the spans and the installation type that the architect wants to use. Again, working with the architect. What kind of roof system does he want? Is he using insulating fill or not? What kind of insulation is he using? That will be a factor in deciding which deck you use and also what span you want. Beware of special requirements such as acoustic criteria. A lot of architects are really enamored by these acoustic decks, where if you're in an auditorium like this and your deck is exposed, you can get the acoustic treatments on the decks that get much better sound rating classifications than the plain old form decks or roof decks. Ensure that the span limits are as required in the factory mutual or underwriter's laboratory, depending on what your project warrants in discussion with the architect. Choose the gauge to carry the load with the spans that you got. Specify the depth gauge and deck type. If standard, if you're using a standard deck, or in rare cases you may get into a non-standard deck application where you have to put the properties of the deck you want on the drawings and let the various deck manufacturers come up with something. And of course, you can only afford to do that if you have really large square footages where they can afford to give you a special rolling of the deck. Choose the proper minimum attachment requirements, either for uplift or whatever the factory mutual or UL might require. And then, of course, you got to pay attention to galvanized or painted finish. So those are some of the things that we as structural engineers, even though we're not the architect, we have to discuss these kind of things with the architect so that we get the right deck specified on our drawings. Form deck we talked about a little bit. We've done a lot of school systems that are floor systems in schools that basically use that same 9/16 core form deck, or sometimes the 1 5/16 inch deck thickness. Put the bar joists at 2 foot to 3 foot spacing with 2.5 inches of concrete over the total slab thickness being 2.5 or 3 inches of concrete, and many millions of square foot of schools are built on that kind of construction, all with form deck. Form deck, thin slabs with bar joists is probably still today a little cheaper than composite decks with composite beams at 8 or 10 foot on center, based on our area anyway. They still tell us bar joists are cheaper, believe it or not. I guess those bar joist folks price their product just so they're always a little cheaper than composite beams. But you can do form deck, you know, that's deeper and spans further. We've used form deck with as much as 4 to 5 foot purlin spacings, putting in anywhere from 3 to 5 inches of concrete on there, depending on what the loading situations are. And then you reinforce that slab just like a conventional concrete slab, because remember, your form deck doesn't act like any reinforcing. It's just a form. For roof construction, if you're going to put lightweight insulating concrete on the roof, you got to always remember to use a vented deck. That is, the form deck you have has little vents in it on the underneath side that allow the moisture to drain out and the insulating concrete to cure. I've seen engineers make the mistake of not specifying a vented deck. The contractor goes and puts insulating concrete on there, and guess what? The insulating concrete never dries. It always is mushy because there's no way to vent the water and the moisture out of it. It take weeks and months for it to dry properly. So vented deck is a very important thing to specify when you're using insulating concrete. And again, you got the whole issue of, do I use galvanized, G60, G90, or phosphatized painted? Normally for roof construction, we always go with the G90 because of the risk of corrosion. This talks about, again, the hurricane class requirements for either welding or screwing the flutes down. Just be real careful of that. And you know, some engineers just don't say anything in their specs about how to fasten the deck down. And believe me, if you do that, the roofing contractor is going to give you very minimum. You'll be lucky if you get SDI minimums. So if you're in a high wind zone, you want to be sure you specify in the deck specification what the fastening method is and what the spacing of the fasteners is at corners, at eave lines, and then in the field of the roof. You don't get anything you don't pay for. Okay, we're going to move next into a discussion of diaphragms, which I think is an interesting area for a lot of engineers because they don't have much exposure to it. But before we do that, I'll open up to any questions anybody might have about metal deck. That was pretty mundane stuff, recognize that, but again, important for young engineers and who are being thrust into these projects without much background. Yes, sir. Oh, I see. So I see. Wow. Everybody hear that? The gentleman is basically relating one of those stories that you tend to experience and then never forget, right? Probably caused you a lot of problems, right, on your project. The situation where a contractor had a kerosene or a heaters in a building that got all the oil all over the bottom of the deck that then had to come back and paint it, and then the paint didn't stick, so they had to go back and clean it. Something to maybe put in the specifications. Yes, sir.
Kind of a, I guess no question, stupid question, but my deck catalog is muchos years old. And just like my bar joist catalogs are. Are there new ones out? I mean, I know I can get them, but have they changed much?
Yeah, they actually have, particularly the bar joist catalogs. I would encourage you, because OSHA has come up with a lot of new requirements on bridging and so on. And the bar joist people are maybe creative is not the good word, but boy, they are very conscious of their product and try to get the most for the least. And so the joist specifications have changed slightly, and you can get all of this online now, by the way. I just downloaded onto my hard drive just to carry it around with me because I travel so much, the new Mullcraft catalog. So you can go to the Mullcraft, and they give you a place where you can download the entire bar joist catalog, you can download the entire composite deck catalog, or you can download the roof deck part, whatever part you want, and just carry it around with you. Well, you've probably been lucky. There are snakes out there in the grass, and it's always good to read the latest stuff, particularly for your specs. Yes, sir.
In the roof, you said that they could use the powder pins or the actuated pins for the composite or for the non-composite deck. Is it permissible to use those pins in composite decking for the securing of the deck to the member, whether it be a beam or joist or whatever?
I don't think I've ever seen pins used on composite deck. I've seen them used an awful lot on roof decks. I can't think of anything that prohibits it. Does anybody else know? I normally just see the puddle welds. That seems to be the most common.
A lot of them are going to shot pins.
Yeah, they are now. They have these automated guns now where the guys can stand up and actually shoot them down. I know there's some real clever guns that have come on the market now for some of the decks that crimp the deck now, particularly on the side lap fasteners. It used to be if you crimped a side lap fastener, you get almost no diaphragm capacity with that. Now I think Merco has a product where their crimping is a patented process, and you can get very good diaphragm capacities with their side lap fastener that you couldn't get before. So I don't think there's anything that prohibits it. Yes, sir.
Just a comment about the fired-in nails. One of the experiences we had was with the early fired-in nails through Hilti. They needed a lot of on-site experimentation because the various hardness of the steel affected the pin type they chose and the power they used to drive the pins in. And I think it's improved with the new specification, the A992, being a more consistent material, but they had problems where they were having to reset up in various areas of the work to get the pins to actually hold on site.
Interesting. Well, I had a situation that this might caution you folks getting into. We do a lot of long span roofs in our practice, and frequently we're called upon, the architects like these curved decks, right? These curved roof surfaces. And so if you're using a roof deck that has to be curved to match the curvature of the frame, then you frequently find yourself in a situation where the top of the purlin might be here, and then the deck's coming across it at an angle. And so you got to do one of two things. You got to put a continuous bent plate all the way along the member to get exactly that right angle so that your deck lays flat, or you have to live with a small gap between the bottom of the deck and the top of the purlin. And one of the things that we had to do on a project is, it was Hilti, they had to come out, they wouldn't guarantee the capacity of their fastener unless the deck was allowed to bear flat on top of the steel support. So when they realized that they were going to likely lose the project over this discussion to their competitor that was Builder Supply, who also does a power actuated fastener, they quickly came on board and came out to site, and we actually did a little program where we tested putting the deck down on a non-flat surface and then actually doing some load tests to see if we could get the capacity. So I'd caution anybody that's going to get into that situation to check it out before you just accept it, because if the gap gets too big between the bottom of the deck and the top of the steel, then you're definitely going to be putting a bending into that fastener that is not accounted for in the tabulated strengths. So just another little gotcha there. Okay, we'll move on then into how are we doing here, Steve? I guess we're doing pretty good. Time? Okay. How about diaphragms in steel buildings? And again, I think this is an area where we engineers don't get much training. Does anybody know of any books out there that tell you, in detail how to design diaphragms? There's one that the Steel Deck Institute now finally put out that's authored by Larry Luttrell, I think his name is, from West Virginia University, who did a lot of the research, but you don't see it talked about much in textbooks. You see it in metal deck catalogs a little bit, diaphragm tables, but anyway, this is one of those things you got to learn on the job. What are diaphragms all about? And really in wind climates, it's not all that important. You kind of get your diaphragms for free. But boy, when you get into a high seismic zone, you can get very high diaphragm shears that have actually shown in earthquake reconnaissance after earthquakes that have caused buildings to fail in one way or the other. And so diaphragms, I think, are an important element. We certainly rely on them, and so we need to know a little bit more about them. We're going to talk about the role that diaphragms play, the types of diaphragms, some design procedures, diaphragm deflections, how you can calculate some deflections when you need to, lateral analysis and diaphragm modeling issues. There are some very important issues that I touched on earlier that we'll expand on. And then potential diaphragm problems that engineers need to be on the lookout for, because they are out there. Okay, obviously the role of diaphragms is to distribute lateral forces to the elements of the vertical lateral load resisting system, or the VLLR. Diaphragms tie the building together as a unit. The diaphragms tend to behave as a horizontal continuous beam spanning between and supported by the vertical lateral load resisting system. So you can think of a diaphragm as nothing more than a deep beam. It spans horizontally between the braced frames or the moment frames or whatever, the shear walls or whatever your lateral load resistance is. The floor itself acts as the web of this continuous beam, and then the members at the floor edges act as the flanges or the chords of the continuous beam. So when you're doing a diaphragm that has high loads in it, you need to think about putting an edge angle or that acts like the cord, or you need to think about attaching the deck to the spandrel beam, where the spandrel beam becomes the cord of the diaphragm, if you will. But if you go that route, then you got to be sure that the connection of the spandrel beam to the column is able to carry the diaphragm force through the joint, through the column to the other side. So that starts to be a connection issue then. Diaphragms are critical for stability of the structure, as the leaning portion of the structure gets stability from the vertical lateral load resisting system throughout the diaphragm. If you have a building that's 200 foot square in plan and all the lateral load resistance is at the edge, and you got all these interior columns, well, we know that columns aren't built plumb, right? Even the Code of Standard Practice says you can erect a column that's out of plumb by L over 500. It's still acceptable. So you got all these columns that are leaning maybe various directions, and they're imparting a lateral load. Whatever the vertical component of load on that column is, when it's leaning, it produces a horizontal shear. Well, that horizontal shear piece, a portion of the load, has to get to the lateral load resisting system, which is providing stability for the building. How does it do that? It creates a shear in the diaphragm. So without even knowing, you might not have realized that your diaphragms are doing more than just acting as floor elements spanning from beam to beam. They're subjected to in-plane shears that are helping to provide stability for the building. And so that's a very important function.